Hi, I'm Beth Wilson. I'm one of the hosts of STEM in 30, a television program for middle school students produced by the National Air and Space Museum. Today, for our live chat, we will be talking about the Chandra Space Telescope that launched 21 years ago today. Our guests to talk about this are NASA astronaut Eileen Collins, Rodolfo Montez, or Rudy, who is an astrophysicist at the Smithsonian Astrophysical Observatory, and Annie Blackwell, who's currently a graduate student at the University of Michigan and who worked on a Chandra project while she was at the Maria Mitchell Observatory Research Experience for undergraduates. I want to thank you all for joining us today. Those of you who are watching online, please put your questions in the comments section. We'll get to as many of them as we can. If you tell us where you're watching from, maybe we'll even give you a shout out. Today, I want to start with Eileen. Eileen, Chandra is a space telescope, which means someone had to put it into low Earth orbit. And on STS-93, you became the first female shuttle commander, and you and your crew placed the telescope into orbit. So do you want to tell us what you were doing today, 21 years ago?
Yeah, it was a great day. It was an exciting day for myself and my crew. We had been training for the mission for over a year, and we had many delays along the way because the company and NASA that was building the telescope wanted to make sure everything was perfect. So they were testing, and fixing things that maybe weren't exactly right. Good thing they did that, because Chandra was built for 5 years. And it's been up there now for 21 years. So it's doing so much better than we originally had planned for it. But what were we doing that day? Well, first of all, my crew had to go through a big sleep shift, meaning 12 hours sleep shift. So instead of waking up at, for example, 6 in the morning, we were waking up at like 6 o'clock at night. And we knew we were going to have a long day. So we slept right up until the very last possible minute. It took us seven days to get that sleep shifting and get stabilized. So we woke up and had breakfast sometime around 6 p.m., suited up, went out to the pad. We had 2 launch scrubs. So when you go out to the launch pad as an astronaut, you got to be ready for either one, the launch or a scrub. But everything went fine that day. Well, we had a couple of potential threats for a scrub due to some communication issues, but we eventually did launch. Maybe it was a little bit after 12:30 p.m. It was a night launch. Right after liftoff, we had a electrical malfunction, and I can talk about that later if you have questions. We also had a main engine leaking hydrogen, which we did, as a crew, did not know about. We learned about it later that day before or after the Chandra was deployed. So even after we launched, there was a possibility that with these malfunctions that Chandra may not have made it to space that day. We trained for aborts, hoping that we'd never have to do one, because Chandra was the heaviest payload ever launched on the space shuttle. And for the crew to do an abort and bring that very large telescope back would have been a challenge for the performance of the shuttle and the flight control system. But it was certified to safely do that. But we didn't have to. We were happy we went up and made it to space. So a very long day for the crew. We got the shuttle secured. We got the payload bay doors open. Katie Coleman and Michelle Tonini were the 2 crew members that deployed Chandra. They went to work right away, running checkouts on the inertial upper stage, as well as the Chandra, the ground teams, up in Cambridge, as well as out in California. It's Sunnyvale. The Sunnyvale team was in charge of the inertial upper stage. They were sending commands. They were doing their checkouts also. We deployed Chandra right on time. It was a very happy moment for the crew. By the way, we had to fly the moment of deploy, although it was a wonderful moment that we said, hey, we finally got this telescope in space. We still had to fly the shuttle away and get in a position for when Chandra did their upper stage burn to go to the higher orbit. We had to be in a safe position and fly the shuttle away. And it was a very long day. The crew was very happy. And from that moment on, we were just waiting for another month or so before first light, because we were knew that Chandra was going to be so far away we wouldn't be able to go back and get it. It was going to be so far away from Earth, about a third of the way to the moon. I think the shuttle did not have capability to go up and get it. So that's just a brief synopsis of what we did on day one. Hopefully that'll give you some information to ask questions later.
Thank you. Rudy, why is this space telescope so important, and how do you use it in the work that you do?
Thanks. One of the reasons it's one of the most important telescopes is that most of the matter in our galaxy, the ordinary matter, is very hot. So it's not seen in optical telescopes. It's not seen in infrared telescopes. It's only revealed in X-rays. And it's only revealed in X-rays when you get to a higher orbit, like Eileen was talking about, because you need to be above the Earth's radiation belt, and you need to be, in order to have long observing times. And so that's why it's one of the more important things. It reveals so much about the universe: explosions, stellar death, black holes, matter around black holes. It even reveals the matter between galaxies that's sloshing around in space. It's quite remarkable, and there's so much science that you can do in the X-ray, and you can't do it in any other wavelength. And you can't do it in optical with Hubble. You can't do it with Spitzer, the other great observatories, but you can with X-rays. My work particularly studies the dying stars. They're really interesting. I think they're very interesting. Dying stars like our sun, what will happen to them? The X-ray mission reveals gas that we don't see otherwise, and it shows us how those processes affect the shapes that we see and as those stars die.
Annie, do you want to tell us what about the project you worked on and a little bit about your studying? And by the way, somebody has said, and it's probably a family member, that they're so very proud of you. So tell us what made them so proud, Annie.
Well, thank you so much. So about 2.5 years ago, I actually started working on Chandra data, and Rudy was my advisor. So he's the one who introduced me to the field. And we studied supernova remnants, which are these structures resultant from the death of some of the most massive stars. And of course, these structures emit light all over the electromagnetic spectrum. But in X-rays, we see the hottest and the most energetic parts of these structures. So we were looking for anomalous energy features to give us a little more insight into what the dynamics are going on with the gas. Are they moving in funny directions? Where are some of the elements being held? And it could also enlighten a little bit about the progenitor star, which is the star that eventually went supernova. And I actually love this work so much, I continued to study X-rays using Chandra in graduate school. So I'm still using Chandra now, and now I study some of the largest scale structures in the universe, which are galaxy groups and clusters. And it's hundreds or thousands of galaxies that are held together by gravity. And they're surrounded by a very, very hot cloud of gas. And we call this the halo. And that halo can be upwards of 70 million degrees Fahrenheit. And Chandra gives us not only photos of these objects, but also spectra. And so my work has been involved with studying these spectra and studying the elemental composition and the abundance of certain elements in these supernova remnants, and now in galaxy groups and clusters, identifying how much iron, for example, could be in these objects.
Well, we have a lot of people watching from Harrisonburg, Virginia, Albuquerque, New Mexico, Oklahoma, Georgia, Kentucky, England, Germany, and New York. And here are some of the questions that are coming in. Eileen, someone would like to know, did you understand how important the telescope would be when you were on the mission?
Yes, without a doubt. First of all, I'm kind of an astronomy junkie. I have been since I moved to Oklahoma when I was 21 years old, and I saw these big, beautiful dark skies. I could see the Milky Way, and I just bought a couple of telescopes. I subscribed to Astronomy Magazine. I joined Astronomy Book Club. I was just a huge, I want to say, junkie for astronomy. And also cosmology. I became fascinated about, where did the universe come from? Where's it going? And when I was about maybe 2 years, it might have been 1997, about 2 years out from the actual Chandra launch, I was looking at the flight manifest and I saw it that it was coming up on the shuttle flight. Now, astronauts normally do not ask their boss to fly on a certain flight. That's not part of the culture. You don't do that. But this one was really working on me. So I ran into my boss in the hallway and I was like, hey, and I dropped a little hint, sure would love to fly that mission. And I was assigned to the flight not shortly after that. So I had a huge passion for astronomy. I can't answer the questions like Rudy and Annie can, but I wanted to work with that community. And I thought that would be really neat to get to know the people that do that work. And to actually, I mean, I feel like by taking up the telescope that I've been part of actually learning more about the universe. You know, I was a little part of making that happen, and so was my crew. All of us were. And I think we all felt the same way, that we knew how important it was. We trained over and over and over in the simulator, training for malfunctions, in the shuttle training aircraft. I practiced in case we had to do an abort and bring the Chandra back. I practiced over and over again. Landing with such a heavy payload, such a aft center of gravity, it was a little bit tricky to fly the shuttle simulator with the Chandra simulated in there. And I wanted to make sure that we as a crew didn't do anything to hurt the mission. We wanted to do it perfectly. And that was the purpose of the training. So to answer your question, yes, I really knew how important it was.
Maybe I'm going to ask Annie this one, since you're currently working with or have been exploring all these different telescopes. Can you tell us, you know, what's different about an X-ray telescope like Chandra and then something like the Hubble telescope?
Yeah. So, I mean, X-rays are some of the most energetic photons that we have, and we can see there's gamma rays above us. X-rays are right up there. And so if we were to try to look at an X-ray object or collect X-ray photons with an optical telescope like Hubble, the X-ray photons are so energetic that they would actually just shoot through the mirrors of Hubble, and we wouldn't be able to stop and collect them at all. So we had to completely revolutionize the way that we collect data when it comes to X-rays. So Chandra is built where it has like these circles, paraboloids and hyperboloids that are stacked inside each other. And so as these really fast X-rays are coming into Chandra, they ever so slightly graze off these metal spheres. And they're redirected twice, and that slows them down just enough to get collected so we can measure it. And so we're actually measuring a single photon at a time. So we get the position where it is in the sky and the energy measurements.
Rudy, we're showing some of the photographs that you provided for us of Chandra. And I'm going to ask our producer to go to slide 12, which is Jupiter emitting X-rays. Can you tell us a little bit about that photo and why it's important, and what are we looking at?
Right. So Jupiter, I mean, Jupiter is a source of X-rays, which is not something you would think about because it's a planet, and it doesn't have these million-degree gases that we've been talking about. So it's quite a surprise to see X-rays from a planet. We've also detected X-rays from Mars. We've detected X-rays from Pluto. I think it was like 1 or 2 photons whenever the flyby happened of Pluto. We pointed the telescope at it and we're surprised. But most of these X-rays are coming from interactions between our solar wind. So our sun is constantly throwing material off into space. It's energetic particles. Those energetic particles can interact in a variety of ways. They interact with our own magnetic fields and create the aurora that we see on the Earth. And it turns out the same thing is happening in Jupiter, but Jupiter is much more massive and its magnetic field is much stronger and bigger. And so it creates quite energetic processes that emit X-rays. And that's what we're seeing in those images. We're seeing the X-rays coming from that Jupiter's aurora.
Wow, that's really interesting. Rudy, your twin sister Ruby is watching with your nephews, and they're loving it, just so you know. We also have people watching from Atlanta, Georgia, Guatemala, California, South Carolina, Baltimore, Queensland, Wisconsin, Brazil, Sri Lanka, India, Massachusetts, Johannesburg, and Ohio. And we also have a school in India that is watching, and they wanted a shout out, but they didn't give us the name of the school, so I don't know what to say. Rudy, this may be for you or Annie. What causes a supernova, and how does it make a super explosion? Billy would like to know. He is from California.
Annie, do you want me to start? I'll start.
Yeah, go for it.
I mean, a star like a more massive star like our sun will end up in a supernova. And what's happening is that you're essentially losing the battle with gravity. The star itself is. So constantly throughout the star's life, it's struggling against gravity, which wants to compact it and bring it all to a point or to a as dense an object as it can. It wants to put all that mass into that dense object. During the life of a star, the radiation that it generates from the heat and the fusion happening in the core will push out, and that creates an equilibrium or a balance between those two forces. And what happens towards the end of a star's life is that you start to lose to gravity, and you start compacting, and you start just pushing things so close together. They're supported ultimately by degeneracy pressure at some point, which is all the electrons, they can't occupy the same space, and so they're just there pushing against each other, which a lot of the Nobel Prize work went to Chandrasekhar, who the telescope is named after. But if you have way more mass than that limit that Chandrasekhar mentioned, then you actually start to push the star beyond its limits, and it will collapse onto itself and release this tremendous amount of energy that is the start of the formation of the supernova remnant. And sometimes you leave behind a black hole, sometimes you leave behind a neutron star, and that's that progenitor that Annie was talking about before.
Eileen, someone would like to know which mission was more exciting for you, the Mir Rendezvous or the Chandra? They said you had the biggest smile following STS-93.
Oh, well, that's an interesting comment. I've never heard that before. I think that for me, personally, the biggest difference between the two missions on STS-63, which was 4 years prior to the Chandra flight, that was my first flight as a pilot, whereas the Chandra was my first flight as a commander. So that was a huge difference for me. My role was different. The other big difference was STS-63, first flight, was my first flight in space, and something that I had been wanting to do ever since I first heard of the Gemini astronauts back in the 1960s. I was a little kid. I wanted to go up into space. But that was a very hard mission. So if I was smiling, I'd like to know when I was smiling, because I worked so hard on that flight. And the other thing about that first flight, because I was the first woman pilot, my friends who are women pilots were saying, Eileen, come on, do it for us, which put a lot of pressure on me. It's like I didn't want to make a mistake. I wanted to make sure that I was setting a good path for the women pilots to follow me. Now, on the Chandra flight, being the commander, you don't just have that function of being the commander, which is, you're in charge of the making sure the crew is trained, your schedule, you're working with all the managers, and making decisions for the flight. You're also on the flight systems-wise. You're in charge of the computers, the environmental control system, and just a variety of systems. But the other thing about that flight is really having the position of being the commander. It's a lot of responsibility, and I think I was a lot more serious on the Chandra flight. You feel that sense of responsibility. If there's any failure, that ultimately falls on your shoulders, whether you did it or not. It falls on your shoulders because maybe there's something. Maybe I could have anticipated this. Maybe I could put some procedure in place to prevent this from happening. So you're constantly thinking, what can go wrong? Are we missing something? And so you've got that. Maybe sense of responsibility on your shoulders. But I think in a kind of a strange sort of way, I do enjoy having that responsibility. I think it's just part of the way that I am. I can look back on it now, and I feel, I think a real sense of pride that the mission went so well, not because of me, but because you really sense the teamwork. And we couldn't have done it. Obviously, when you're the commander, you really see that. It couldn't be done without the operational side, without your crew, without the trainers, without mission control, NASA management. I'm going to say, the people that built the Chandra back when it was called AXAF, it was built by TRW out in Southern California. And then you had the inertial upper stage, the folks from the Air Force out at Sunnyvale. And then all the operation folks up at the Chandra Operations Center. I mean, it was just one big team. And we had a lot of bumps in the road along the way. And sometimes you come home at night, you're scratching your head like, oh, what are we going to do about this? But it all came together. So I think, it's really hard to compare the two flights. I mean, I wish I had a better answer to your question, but they were so different. Not only the nature of the flight, they were on two different orbiters also, but not only the nature of the flight, but I think the role that I played in the flight.
And
thanks for the question, though. Good question.
Anytime you go into space, it's always different. I mean, it's not just you're running to the grocery store by any stretch of the imagination. Annie, if someone would like to know, what would we see if Chandra pointed at our star, the sun, or has it even done that?
Ooh. Rudy, do you know if it's pointed at our sun? No, that would be terrible.
It would be terrible. It would be bad.
So Chandra is powered by solar panels. And in one of the photos of Chandra, you see like the front of Chandra and the solar panels as well. And that would be terrible because then Chandra would be pointed directly at the sun. So no, Chandra has not taken a photo of our sun. But most stars, they're lower energy, they're cooler. So they're closer to our sun. Our sun is an average type star, and they don't really emit X-rays. But some of the higher mass, some of the really hot, large stars, they will emit some X-rays.
Rudy,
the sun's activity. Oh, sorry. The sun's activity is very mild for X-rays. It does emit X-rays, but it doesn't have a lot of X-rays coming off of it.
Well, Rudy, let me follow up with this. Why is it hard to observe X-ray sources in visible wavelengths?
Because if when the gas reaches 1 million degrees and higher, you start to just see the X-ray emission coming from it. You don't see a lot of optical emission. That doesn't mean there's no optical emission, or visible light, but it means that there's very little of it, and most of that emission, most of the photons are coming out in X-rays. So if you look at like a patch of the sky where a supernova remnant is, you might see a little bit of H alpha, which is a hydrogen gas that's been excited, but it will be very dispersed and very faint. Whereas the same field of view with the X-ray telescope like Chandra will reveal this amazing structure behind the supernova explosion.
Eileen, this is about private space companies, and the viewer would like to know, will private space companies have scientific payloads, or are they going to focus mainly on manned flight? Do you know the answer to that?
Well, I think I can speculate a little bit. Yes, I think the answer to that is yes. The thing about when you think about private companies, they're normally looking for profit, and maybe not in the near future, but maybe off in the distant future. So the reason the governments do this research first is because there's really no motive for the private sector to initially go out and do science. But once the governments prove that yes, it can be done, it can be done safely, it can be done successfully. If there is a profit motive seen, then I believe private industry will follow. But we already see that happening in medicine. There's research going on the space station right now, developing vaccines, for example, studying the human body, protein crystal growth, things that we can do in space. So I think that's a good question, and it's something that we can think about as we go off into the future. Personally, I think the immediate profit motive for private companies is in space tourism, which I believe is going to be extremely successful. And you see some of these companies like Virgin Galactic, for example, that's probably the closest to flying private people in space, they're going to go suborbital. Okay, they're not going to go around the Earth. They're going to do suborbital, which will be less than 1 hour. But it's a good step in the right direction. You know, people will get to experience microgravity for a short period of time. They'll get to see the stars at noon, for example. And then someday people will be able to fly in orbit, which is where the space station is. I mean, that's really the goal, is to go up into orbit so you can spend days at a time and longer. The difference being, to go into orbit, you need a heat shield. For suborbital, what Virgin Galactic's do, you don't need a heat shield. You go up, you come down. I mean, you might go to 60, 70 miles, but to go up to 200 miles, now you're in orbit. To come back, to re-enter, very, very hot, you need a heat shield. So I don't really have an answer to that question, but I think it's something that we can think about, and I think maybe farther off in the future, maybe not in our lifetime, we'll see a lot more research taking place, maybe on the far side of the moon.
That'd be really cool. I'd go there. Annie, somebody would like to know what you're working on now for your PhD research.
Yeah. So I talked about this a little bit, but I'm studying galaxy groups and clusters, some of the largest structures in the universe, hundreds of thousands of galaxies held together by gravity, and they're surrounded by very, very hot gas. And this gas we can only see in X-rays. So I have to use telescopes like the Chandra X-Ray Observatory to study it. And my focus with this gas is trying to get accurate measurements of the temperature of this gas and the metallicity, which is how much metal is in it exactly. And for that, we use the iron line. It's got a very strong peak in X-rays. And I know the one I'm looking at is at about 5.6 keV, and that's kiloelectron volts. It's what we use for our energy measurement. And I'm trying to narrow down this relationship between how much iron is in the halos of these galaxy groups and clusters to how many stars are actually there. Because we think it's a known relationship, but we're finding out we don't really know it. It's a little unexpected. So that's what I'm doing right now. And it's going to evolve in the next coming years.
As school will do to you, correct?
Absolutely.
Rudy, Nick, who is age 7, would like to know if black holes ever die out. And I think that once you answer his question, Chandra worked on getting that photograph of the black hole. So if you want to just talk a little bit about black holes and if they die out, and then how Chandra helped Event Horizon with the black hole photo.
Okay. Thanks for the question, Nick. That's a hard one to answer because, like, what does it mean for a black hole to die out, I guess, is a more difficult question. I don't think it will necessarily die out. There are things that will last the lifetime of the universe. Those things include our sun when it has died. The white dwarf will continue to just smolder away like a piece of charcoal in space forever. Some very low mass stars will live most of their lives just as they are. And so a black hole will probably, if we reframe the concept of it dying out as in how much light is it emitting that we can see, well, it's never going to emit any light, but it's going to gobble up the material around it. And that material is a finite resource, and so it will eventually run out of material to fall into it and to heat up, and we see it as it's heating up before it either enters or escapes the vicinity of the black hole. So that's that. When you run out of that reservoir of material and you're no longer heating it and creating X-rays, then we will no longer see it, and maybe that's an indication of it dying out. When the Event Horizon Telescope did its imaging of the black hole in the M87 galaxy, Chandra and a bunch of other space observatories also looked at it at the same time, and so we built this multi-wavelength view of what was happening at the time of that image. Chandra doesn't see that far. It doesn't have, it's the best X-ray resolution telescope that we have in space and have ever put in space, and might be the best for the foreseeable future, but it doesn't have the resolution to actually peer into that black hole. That black hole is so small on the scale of Chandra's visibility that it's all within 1 pixel of our instrument. But what we do see is all the material around that's swirling around, that's being heated by the energetics in that around that black hole, and we see the jets that are flying out of that black hole that are being driven by the winds that are coming off of that heated energetic material and then being thrown into space. And we see all of that. So really, when you look at the Event Horizon Telescope image, you're looking at such a small part, but you got to remember that it's happening inside of a big reservoir of material that the Chandra X-Ray Observatory will allow us to see.
Eileen, you talked a little bit about how many different people were involved in creating the telescope. Can you tell us about the team that it took to put it into orbit, and how did they deploy that?
Well, okay, so as I mentioned earlier, I kind of, from where I sat, I kind of saw it really as 4 teams, but I was thinking but there were many more, but I think about it more of their locations. So there was Kennedy Space Center, which prepared the shuttle, and when the Chandra arrived, they integrated the Chandra into the shuttle and got that ready for launch. And then there was the team up in Cambridge in the Boston area that was part of the Chandra Operations Center. And then there was the IUS, the Inertial Upper Stage Team, which was Air Force people out at Sunnyvale. So they are in charge really of the operations of the IUS and getting that burn off, which happened, I think, within the hour of us releasing the Chandra from the shuttle. The IUS, had a single solid motor on the back of the Chandra, and that's what took it a third of the way to the moon. And we worked with the Air Force folks on that. And then there was the operations folks in Johnson Space Center in Houston, and that was made up of the mission control, which has a flight director, flight controllers, and they are responsible for the various shuttle systems. But there was also a payload officer there. His name was David Brady, and he was he was like our primary contact person as a crew with all these teams around the country, David Brady. And Brian Austin was our flight director, and the two of them played that role. And we also had our team of instructors. And then, of course, there's the company I mentioned, TRW, that built Chandra out in Southern California. So as a crew, I mean, before the mission, we would travel around and meet these folks. And then there were more teams like the Space Shuttle main engines, the Space Shuttle external tank, the solid rocket boosters. And then there were, of course, the people that worked on the science. And we really didn't work with them as much until after the flight because it wasn't as essential for the crew to understand the science. We did have an astronomer on the flight, and that was Steve Hawley. And Steve has a PhD, and he's currently teaching in Kansas. He's back in the university environment again. It was great to have Steve around because whenever someone asked the crew a question on science, we'd all look at Steve and have him answer it because we didn't want to kind of tap dance around the science. And we did have, I mean, even before the flight, questions on what was the science going to do. So I think I hit all the main teams, but it's really important for the crew, as busy as we are. And by the way, the 2 crew members that deployed Chandra, Katie Coleman and Michelle Tonini, also had to train for a spacewalk in case there was a malfunction while we were deploying. They were ready to put on their EVA, extravehicular activity suits, and go out and fix whatever the problems were, which mostly EVA type failures on the inertial upper stage. Chandra, by the way, by putting Chandra on the space shuttle, gave it it was a risk management decision, among other things. If you launch on a unmanned rocket and there's a malfunction, you don't have astronauts there that may be able to fix the malfunction. You can take a look what happened in the Gamma Ray Observatory, which was launched on the shuttle. Their high gain antenna did not deploy. I think this was in 1993 timeframe. And Jerry Ross went out on a spacewalk, and all he needed to do was shake that high gain antenna a little bit, and then it deployed. So it was something as simple as having an astronaut ready to do a spacewalk. that saved the mission of the Gamma Ray Observatory.
We have folks watching in Arizona, Dallas, Texas, San Francisco, Knob Noster, Missouri, Florida, Vienna, Virginia, Louisiana, Memphis, Tennessee, where I grew up, and in Maine. A lot of people, and Rudy, I'm going to ask you this, a lot of people are asking, what is the most remarkable discovery that Chandra has made?
Oh, I'm going to make a lot of enemies if I pick one thing.
Oh, good. This is a lot of times we get arguments in the comments, whether it's Star Wars or Star Trek. So why don't you see if you can start a Chandra war in our comment section?
I mean, this is a very difficult question. It's because some of the early work that we've done is looking at stars that are forming in star forming regions, and just looking at them for a very long time, watching their light change and watching and characterizing young stars in stellar nurseries. And so as far as like the how many objects you've actually studied, there's so many stars in those studies. But then if you talk about the mass in the universe, then the galaxy clusters and research with the galaxy clusters is some of the most interesting, and things that only Chandra can do because of its spatial resolution and its X-ray sensitivity. But my favorite is probably looking at clusters and looking at the cluster motions in the bullet cluster and identifying where the hot gas is, which is most of the baryonic matter, and then combining that with other wavelengths, and in addition to that, microlensing to get a mass map, and seeing how the mass and the X-ray gas are not quite in line with each other, and how that tells us about the existence of dark matter. I think that's one of the more direct measures that we have to indicate that dark matter exists in our universe.
Annie, how is Chandra different than the Einstein X-ray telescope?
You know, I've never worked with the Einstein X-ray telescope, so I really don't know much about it. The other X-ray telescope I work with is XMM Newton. And I mean, like Rudy has said several times, Chandra has an incredible spatial resolution, so you can get a lot of details. But like compared to like XMM Newton, which is the only other X-ray telescope I know, XMM Newton has a much larger field of view, but much less spatial resolution. So it's really a give and take on what science you're doing and what telescope is going to benefit what you're trying to look at.
I can address that a little bit also.
Okay, great.
Einstein was well before Annie's time, and it was one of the first imaging telescopes, X-ray telescopes, that was put into orbit, and so it actually paved a lot of the way for the technology and that we used in Chandra, and so that mission was quite helpful for Chandra. It didn't have the sensitivity, and it didn't have the resolution that Chandra came ultimately put into space.
One of our former employees from the National Air and Space Museum, Genevieve, says hello. And Chandra was the first telescope she worked on for research back as an undergraduate. And she says it's an awesome telescope. Eileen, someone would like you to talk a little bit about the issues that you had just trying to get off the ground. What happened there and how were they solved?
Wow. So I got to think back on this one. So we were in quarantine for a little while. It was supposed to be 7 days, but we went out to the pad. I think we were supposed to launch on July 20th, which just happened to be get my years right, the 30th anniversary of the moon landing. Did I get that right? So the moon landing was 1969, 79. Yeah, so it was the 30th anniversary of Neil Armstrong, Buzz Aldrin, Michael Collins flying Apollo 11. Well, the three of them came to the launch. We had all kinds of people at the launch. It was a nice summer event. And we scrubbed that night. I'm trying to remember. I don't remember what happened, but I do remember we got all the way down to like 8 seconds. And I believe what happened was there was a engineer in the Launch Control Center that saw a sensor in the aft compartment of the shuttle, back where the engines are, spike high with hydrogen. So high hydrogen concentration in the aft end of the shuttle is it's an explosion hazard, a fire. So he stopped the launch, and we went into a launch scrub. And I'm not sure I have all this right. And then but I remember we went back out. So the engines didn't light. So if the engines had lit, we would have to change the engines out, which would have been a 1-month delay. But instead, they just had to change the sparklers, which are those, you see those sparklers before the launch. They're there to burn off any hydrogen that might be leaking around. So 2 nights later, we tried to launch again, and we had a weather scrub. But I remember that night, the weatherman told us we had a 100% chance of good weather. And we went out there and we're laying on our back, watching the, launch countdown. And Steve Hawley said to me, "Did you see that flash? That was lightning." Of course, it's nighttime. And I said, "No, Steve, it's not lightning. We had a 100% chance of clear in a million weather launch tonight." Well, if I remember all this correctly, we scrubbed for thunderstorms. So, and then we went again the following night, and that would have been 2020. I'm getting, because we launched shortly after midnight, the dates were actually different. So it would be like July 23rd on the East Coast, but July 22nd on the West Coast. So the date got a little bit confused there. But we had a communication issue on the last launch attempt, which was over on the Air Force range side. And they managed to fix their problem. But there was a lot going on behind this, because for probably 2 years, even before the crew was assigned, we tried to get a bigger launch window. Because I think the launch window was about 40 minutes, maybe. But if you launched outside of 40 minutes, you would have some risk to getting the Chandra to the place that it was supposed to be. And they were actually talking about expanding the launch window until we get the communication problem fixed. Well, fortunately, we didn't need to do that, but we got the launch off within the scheduled window, which made it easier for the remainder of the Chandra mission. So yeah, 21 years ago, I've flown 4 space shuttle missions, and of all the scrubs I had, they're all starting to get mixed up from one mission to the next. But yeah, thanks for the question. It meant for I think I could write a book on the Chandra launch minus a week, because there was so much going on.
Well, we're almost out of time, so I want to wrap up with the same question for all of you. Someone with, "Hi, I want to pursue a career in space." So here's a question for the 3 of you. What made you want to have your career? Well, actually, there are 3 questions, but it's all about career. What made you so interested in space, and what made you so determined to pursue your career? And Annie, since you're just starting out, we'll start with you.
Yeah.
What about this has got you so inspired?
I mean, space is massive. There is so much that we still don't know about it, and we don't even know to ask questions about so many things, because we just have yet to discover them. And with every new telescope, every new mission, new push, new idea, something brand new gets uncovered and discovered. And there's always something new happening in the field. And to me, that's very exciting. And to get to be on the forefront of those discoveries and say, like, I helped, and then to acknowledge everybody else and all the work that goes into just one of these awesome new finds is just such a treat to be a part of.
Rudy, what about you?
I started an unusual journey when I was studying at the San Antonio College, a community college. I was taking accounting classes. That was my major, and I had a intro astronomy course with Alfred Alanese, and it was so exciting. I was talking about it all the time with my friends, and they're like, "Why don't you just do that?" And I was like, "Okay." So I figured out how to do that, and then I did it, and now I'm here doing it.
I love stories like that, because I actually have degrees in fine arts. and I ended up at the National Air and Space Museum just because I was interested in air and space. Eileen, what about you? How did you get to where you are?
Well, first of all, I want to say I heard Rudy give a talk at Southwest Research Institute was it a year ago? That was fantastic. It was just he was able to take science and give a presentation that was not only easy for everybody to understand, but it was also humorous. And I can't wait to hear it again. But I've always wanted to be a pilot. So I wanted to join the Air Force and be a military pilot. I majored in math. And, the Air Force gave me a scholarship through ROTC as a math major. I was supposed to go in the Air Force and be a computer systems design engineer. That was the job they gave me. But then they opened pilot training up to women. That was 1978, and it was a test program. And they were training women. Before that, it was only men could fly in the Air Force. So signed me up for that. I've always wanted to be a military pilot. But I love science, too. I have always loved science. So I feel like I was able to take all those and combine them into a career. But, I will say, like you mentioned, fine arts, because space crosses all of these disciplines, history, English, languages, international relations, art, writing. You just keep law, medicine, you just keep going on and on. So whatever you decide to do, you can kind of work your way into the space program too.
I will say that a lot of the images that have come back from space telescopes and missions have ended up actually in my artwork. The Juno mission, I've done a lot of drawing and painting from. So there's something for everybody when it comes to space. We are out of time. I want to thank you all for joining us today. This was a really great talk. Next week at 1:00, we will have our teacher chat about virtual learning. We'll have the Teacher Innovative Institute teachers, and also our special guest, Mike Massimino, who fixed the Hubble telescope. He is a great storyteller. Also, if you want to learn more about Chandra and the awesome women involved in the aerospace industry, be sure to check out NASA's new Reach Across the Stars app and website. This free augmented reality app can be used on most compatible tablets as well as smartphones. The app allows you to journey to Mars in 3D with Ellen Stoffen, who is the director of the National Air and Space Museum, and listen to the stars with computer scientist and astronomer Wanda Diaz. Other women featured are astronomers Nancy Grace Roman, mathematician Katherine Johnson, and astronauts Mae Jemison and Sally Ride. So be sure to check that out. And be sure to join us again next week. And thanks so much for watching.